Welcome to a code report solution video. In this video, we're going to be covering the solution to the second problem in our dynamic programming series. The problem is entitled Construct the Array. The problem states your goal is to find the number of ways to construct an array such that consecutive positions contain different values. Specifically, we want to construct an array with n elements such that each element is between 1 and k inclusive. We also want the first and last elements of the array to be 1 and x respectively. Given n, k, and x, find the number of ways to construct such an array. Since the answer may be large, only find it modulo 10 to the 9 plus 7. And it has an example here where it says that if n is equal to 4, k is equal to 3, and x is equal to 2, there are 3 ways that we can construct this array. So n is the number of elements, k is the upper bound of the values that each of our elements can have, and x is the value that the last element should have. So you can see here it shows each of the 3 possible arrays that we can construct. And at the end here it says complete the function count array, which takes the input n, k, and x and return the number of ways to construct the array such that consecutive elements are distinct. And the constraints of the problem are listed below. N is between 3 and 10 to the 5, k between 2 and 10 to the 5, and x between 1 and k as stated in the problem. So let's take a closer look at this example to see how we can solve this using dynamic programming. So here's our example once again, n equal to 4, the number of elements, k, that means our elements have to have the values between 1 and 3, and x is the last value of our array. And note that our array should start with the value 1. So the way that we can try to go about finding a way to solve this problem is to sort of draw a tree of all of the possible values that each element can take at each step based on the previous step. And so to begin with, we're going to assume that x cannot equal 1. So x is always going to be different. The ending element in our array will be different than 1, and we'll come back and cover that case afterwards. So starting with our array, we start with the value 1, and then because this problem states that 2 consecutive elements can't be the same, we know that the next element can't be 1. So that means it can either be 2 or 3. And then from each one of these points, we sort of do the same operation. So when our element is 2, that means the next one can be 1 or 3. And when our element's 3, the next one can be 1 or 2. And we continue to do this until we have 4 elements, and we end up with this. And so the other condition is that our last element has to be equal to x, and x here is 2, so that means the valid arrays are the ones that end in 2, here, here, and here. And those are the arrays that are shown in the problem statement. And I've also highlighted, so I've highlighted these arrays in blue, and then I've also highlighted if n was equal to 2 and to 3, how many valid arrays would we have, possible valid arrays. So with n equal to 2, we'd have 1, and with n equal to 3, we'd also have 1. And so we need to find a way to sort of reverse engineer from each step of this how to get to the next step. And so the way we're going to do that is by classifying sort of 2 different states, which are represented here by our colors. And these states are arrays that end in x and arrays that don't end in x. So we have 2 states. Ending in x is represented by the blue circles, and ending in values that are not x are represented by b. And once we've separated these into states, we can try and make observations about how we move from one state to another. And so the first thing we can do is just basically create 2 arrays for this example that keep track of the values for each one of these A and B arrays for each of the steps n equal to 1, 2, 3, and 4. So we can see here that we construct our array A, which is just how many valid arrays for each length n do we have. So when n is equal to 1, we don't have any valid arrays because we're assuming that our x value can't be equal to 1. In this example, it's equal to 2, so there's no valid ones. But for n equal to 2, we have 1 possible, n equal to 3, we have 1 possible, and n equal to 4, we have 3 possible, which is the answer for this question. And for b, the number of arrays that don't finish in x, it's just basically the remainder. So we've got 1 here, 3 here, and then 1, 2, 3, 4, 5. So now that we have these arrays, we can try and make observations about them. So the first very easy observation to make is that the value of the ith element in A is equal to the value of the B, the element at the index I-1 in our array B. So we can come up with this equation. And if we try and reason about this, it really makes a lot of sense. So it's basically saying how many valid arrays at n equal to I can we have that are ending in x? And because we can't have two consecutive elements that are the same value, that's just going to be equal to the number of arrays that didn't end in x at the previous step, which is exactly what this is saying. So it's saying at our step I, the number of arrays that end in that end in x is just going to be equal to the number of arrays that didn't end in x at the previous step, because we can't have two possible elements. So that takes care of constructing A. And then how do we construct B? We have this formula here, which looks a bit complicated, but it's actually pretty straightforward to come up with this just by looking at what we have. So we figured out how to calculate the number of arrays ending in x. So how do we calculate the number of arrays not ending in x? So what we'll notice here is that if we take a look at sort of this example here, this is where we have an array at the previous step that's ending in x. And we know that because we can't have two consecutive elements, the next element can't be x. So both of these are going to be contributing to the number of arrays that don't end in x. And we can calculate that by basically taking the number of elements that end in x and multiplying it by k-1. K is the possible number of values that we can have. And we subtract 1 from it because we know that we can't use our value that is x. So all of the values can be here except for one of them, which is where we get k-1. So that's the first term, is that all the values that end in x multiplied by k-1's values, which is all of the values just subtracting out the single value x that it can't be. And that gives us, you know, a portion of the number of arrays that don't end in x. And then if we take a look at these three sort of nodes here, when we have an element or the end of an array at our previous step that isn't x, in order to end up with an array that in total doesn't end in x, we can move to any value that isn't x and also isn't the value itself. And that's because we can't have two consecutive values, so it can't be 3. And we don't want this array to end in x, so it can't be 2. So that leaves us with only one value in this example, but in general, it's k-2 values. So all of the values minus x and minus the current value. And we multiply this by all of the arrays that ended in a value that wasn't x. So that's just bi. So this is actually should be bi-1. There's a small mistake there. Times k-2. And that basically covers all of the possibilities of ending with an array that doesn't end in x. So I have these primes here just to sort of summarize. So we talked about how to generate all the number of arrays that end in x. That just makes sense. It's equal to the number of arrays that didn't end in x at the previous step. And then our two components that make up the number of arrays that don't end in x, we have k-1 because it's all of the values except for the one itself, and then k-2 because it also can't be x. And maybe these are actually mixed up too. So a-1 is a value ending in x. So actually, yeah, k-1 is because it can't be x, and then k-2 is because it can't be consecutive. But I guess technically this is correct as also the way it's stated. I guess they're sort of swappable. So hopefully this makes sense. And this is basically the work of this problem. You have to basically derive these two equations, and then once you have that, you can compute the solution in linear time. So this code looks as follows. We're just declaring two arrays, A and B, and then we're initializing the values in A and B to be the initial solution. So ending in x is 0 at the first point because we know that our first element has to be 1. and ending in x is 1, which is just the element 1 itself. And then we basically just loop from 1 to 1 less than n, and we just plug these formulas in. And then you return a, the last element of a, and that gives you your answer. And the reason we're returning a is because we want the ones that end in x. That's what the question is asking for. So if we quickly swap back, I mentioned that we're assuming that our first element and our last element can't be equal. So we are assuming x is not equal to 1. But the problem changes slightly if we can actually have x equal to 1, which we can. And if we have that, the problem switches like this. So I'm not sure if you can notice the difference, but actually everything stays the same. The only thing that's different is that we are now having a0 initialized to 1 because the number of elements that end in x at our initial state is 1, and b0 is equal to 0. And so all we have to do is basically change the initialization values of the first index of our arrays, and then we can arrive at the correct solution. So if we modify the code, it just looks similar to the following. We basically add this ternary operator here, and we set the value of our 0th element in our array A and array B based on whether x, which is our value that we want the last element of our array to be, we use that to set the 0th element of our array. And note that I've added the modulus here that I sort of left out in the previous code. So that's about it. Hopefully this made sense. And yes, this was technically the first dynamic programming solution, even though we've had 2 videos, because the last video didn't really cover dynamic programming. So the last thing to talk about is the time complexity, which for this problem is going to be linear as mentioned before, because we're just doing a single loop over the number of elements in our array.
As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.